A mystery interstellar object that was spotted by astronomers last week. It could be the oldest comet ever seen.
On July 1st, 2025, the Atlas survey detected a faint moving object that followed a hyperbolic path, indicating it came from outside the solar system. Observations showed a coma and a dust tail, signs of active mass loss consistent with comet-like behaviour. Combined optical and infrared measures constrain the solid nucleus to at most a few kilometres across. Spectra revealed common volatile compounds and dust features seen in cold-formed bodies. Teams worldwide tracked its motion and confirmed there is no impact risk to Earth. This rare interstellar visitor provides direct samples of material formed around another star for study. Astronomers are stunned. An object from another star system has slipped into ours. But what kind of traveler is it? And what secrets does it carry across the cosmos? What exactly entered our solar system? Scientists first noticed the object as a faint point of light in survey images. Survey telescopes like Atlas take wide pictures of the sky each night, and automated software searches for points that move between images. When a moving point is found, follow-up telescopes take more pictures and spectra to learn more. For this visitor, teams moved quickly to gather many observations across a range of instruments. The first goal was to measure its motion so astronomers could compute an orbit. To compute an orbit, observers record the object's position against background stars at known times. With enough measurements taken over days, the path becomes clear. Astronomers report a number called eccentricity that shows how the path bends under the sun's gravity. If eccentricity is larger than 1, the path is open and the object is not bound to the sun. This object showed that kind of path and a speed higher than typical solar system bodies. That is why scientists call it interstellar. After the orbit was found, telescopes examined the light the object reflected and the light from the gas around it. Comets show a fuzzy cloud of dust and gas called a coma and often a tail. This object displayed a coma and a tail. Images from large ground telescopes and the Hubble Space Telescope showed how bright the coma was and how dust trailed away from the core. Spectra showed features consistent with common comet gases and solid particles. Those measures let scientists estimate how much material was being lost. Estimating the size of the solid core is not a walk in the park. The visible light depends on how reflective the surface is and how much dust surrounds it. To reduce uncertainty, specialists combine visible light with infrared measurements because dust and warmed material give off infrared radiation. With that data, they set an upper limit on the nucleus size. For this new object, estimates put the solid core at most a few kilometers across, a size similar to many comets in our system. Observers also checked for changes in brightness that match rotation. If the solid core is irregular, it will reflect different amounts of light as it spins, creating a repeating pattern. Data showed some variation, but not a strong, repeated signal that would point to a strange shape or very rapid spin. Scientists also searched for jets or localized vents where gas escapes. Jets can make uneven dust patterns and bright features in high-resolution images. The images show dust distributed around the core and no persistent, unusual jets that would demand a new explanation. Another focus was the composition of the gas. Spectra split light into colors and revealed fingerprints of some molecules. Observers then searched for water, carbon compounds, and other volatiles. The signatures indicated a mixture of common comet materials, with dust and gases typical of objects formed in cold, distant regions. The balance of dust to gas and the speed of dust grains gave clues about formation and how the object reacted to sunlight. Finally, orbit models and continued tracking confirmed there was no risk of impact with the Earth. The path will carry the object through the inner system and then back out into interstellar space. Telescopes around the world coordinated to track it as Earth turned, building a dense set of observations. That global effort gave confidence in the orbit and the physical measures. In short, the object behaved like an active comet from outside our system, shedding dust and gas while moving on a fast open path. These observations offer a rare, direct look at material from another star now. It may just look like another comet, but hidden in its light are clues about alien worlds and their chemistry. Why does this discovery matter more than we think? Why this discovery matters? An object from another star gives scientists a rare chance to study how other planetary systems form and what materials they are made of. When light from the object is split into colors, instruments reveal fingerprints of molecules and dust. Finding water, simple carbon compounds, and other volatiles tells researchers whether the body formed in a cold outer region or closer to a star. The mix of dust and gas shows how much ice the object kept and how it reacts when warmed by the sun. Measuring isotopes, which are different forms of the same element, is especially valuable. Isotope ratios record the chemistry in which the body formed and the temperatures it faced in the early stages. Suppose an interstellar object shows isotope ratios similar to comets in our system, which points to shared chemistry across systems. If the ratios differ, that points to distinct formation paths and environmental histories. High-quality spectra can reveal some of these ratios in gas or in dust, and that gives direct clues about the origin. The amount of dust compared to gas also matters. Comets that formed far from their star tend to be rich in volatile ices and show strong gas emissions when warmed. Bodies that formed near a star can be drier and show a heavier dust signal. By measuring the dust-to-gas ratio and the sizes of grains, scientists estimate the temperature and the region of formation. Grain size affects tail shape in this manner. Fine grains are pushed more by sunlight, while larger grains hold a path closer to the solid core. Understanding how a body left its home system is another key question. Young planetary systems can scatter small bodies during early planet growth and migration. Close encounters between stars in dense birth clusters can fling material into interstellar space. Different ejection paths leave distinct speed and direction signatures that models can predict. With only a few detected visitors so far, each new case helps tighten those models and test how common each path may be. Observing an interstellar object also improves detection and coordination systems. Wide-field surveys find moving candidates and send alerts for rapid follow-up. Large ground telescopes add high-resolution images and spectra, while space telescopes provide steady, atmosphere-free views. Teams in different time zones share work so the object can be tracked as Earth turns. This global cooperation gives denser data and reduces error from any single instrument. Comparing such objects to past cases builds a catalogue of traits to guide theory. One earlier object showed very little gas, while another behaved like a normal comet with clear gas emissions. This range shows interstellar bodies come in varied types and have different histories. Comparing spectra, dust properties, and motion across many cases will allow statistical studies that are not possible with a tiny sample. As the catalogue grows, theories about planet formation, migration, and ejection will become firmer. These discoveries also drive instrument design and mission planning. Scientists study which spectrographs and cameras work best for faint, fast-moving targets. Engineers explore fast-response mission concepts, from small, quick flybys to pre-positioned craft that can change course on short notice. Those mission ideas face real limits, such as launch speed, propulsion options, and short reaction time. Even so, focused mission studies show small probes could return images and spectra that provide far more detail than remote observation alone. Interstellar objects also help test ideas about chemical evolution across the galaxy. Finding common organic molecules or repeated isotopic patterns would suggest that some building blocks are widespread. That result would not prove life, but it would show how raw materials travel between stars and shape planet formation. Each new object adds a data point that sharpens our view of how planets and small bodies form across the galaxy and improves the models scientists use. The work also trains students in fast analysis, data reduction, and international collaboration. building skills that improve science and mission readiness. What observations show, and Michio Kaku explains telescopes collected images and spectra across visible light, infrared and radio bands. Each instrument adds a piece of the puzzle. Visible images show the coma and tail, infrared reveals warm dust and any thermal glow, and radio can detect certain gas molecules. Large ground telescopes captured fine detail in the coma, while space telescopes offered a better view without atmospheric blur. Combining these views gave a fuller picture than any single observation. Michio Kaku, as a science voice, summarized the main ideas for us. He explained how orbit and motion show the object came from outside the solar system, how a coma forms as ice turns to gas, and how spectra reveal common comet compounds. His role was to take complex measurements and make publications so that researchers could follow what instruments actually measured. That explanation helped many people focus on the real information that truly exists. From the images, observers mapped the coma shape and the tail direction. The tail points away from the sun because sunlight and the solar wind push dust and gas outward. Careful measurement of tail features gives speed estimates for dust grains and shows how much material the object has lost. The rate of mass loss can be compared with comets inside our system to determine whether the object is unusually active or typical. Spectral lines gave clues about composition. Water vapor and simple carbon molecules show specific lines that trained instruments can pick up. The ratios of these lines and the presence of dust features.
How amazing is it that we humans have a word for something that literally flies between stars and so far
Suggest a mixture similar to some comets formed in cold regions. Scientists also monitored how these signals changed as the object moved closer to and past the sun. Changes in brightness and in spectral strength showed how the body reacted to warming. A key tool was time series observation. By taking repeated spectra and images over hours and days, teams watched how the coma evolved. That method can reveal new jets, sudden increases in activity, or steady fading. For this object, the record showed accurate activity and a dust production rate within the range seen in regular comets. Observers also looked for unusual chemical species that do not appear in common comets. None were found at a level that would overturn normal explanations. Merging data from many teams required careful calibration. Different telescopes have different sensitivities and resolutions. Scientists correct for those differences and combine the datasets so that brightness and spectral features match across instruments. That process increases confidence in the results and reduces the chance of error from a single instrument. In other terms, multiple independent measures that agree make the findings stronger. Observers also studied the object's rotation by checking repeated light variations. Rotation can reveal shape and help estimate density. Polarization studies of scattered light gave hints about grain roughness and composition. Compared to earlier interstellar objects, this object fits within known comet behaviour, although the differences will guide further research. So far, this interstellar traveller seems harmless, but what if the next one isn't? Could a rogue object from deep space ever pose a real danger to Earth? Could interstellar visitors ever be dangerous? People ask whether a large body from another star could hit Earth. The answer depends on the path and timing. Most objects pass by without risk. Scientists calculate orbits from many observations and can predict future motion with high precision. If an impact path existed, specialists would see it in the orbit fits and report it. The current visitor had a path that misses Earth by a wide margin and will leave the solar system. Defense planning focuses on early detection. The earlier an object is found, the more options are available. Modern surveys scan wide areas of the sky and software flags moving points for follow-up. Upgrades to surveys and new networks will find fainter objects sooner. If an object on a collision course were found years in advance, there are proven methods to change its path. The DART mission tested one method. A spacecraft intentionally struck a small moon of an asteroid and changed its orbit. That test showed a kinetic impactor can nudge a body in space. The technique needs time and accurate targeting, but it has proved the principle. Other options include using a gravity tractor, which slowly pulls an object by mutual attraction, or using engines on the object itself if access were possible. Nuclear devices are considered only as a last resort because of legal, technical, and political limits. A fast interstellar object is harder to intercept. It moves more quickly and arrives with less warning than typical near-Earth asteroids. That makes a rapid response more difficult. Despite that, the current object posed no threat. For practical defense work, improving detection speed is the clear priority. Faster discovery gives more time to study the object and plan a response if needed. International cooperation matters too. A real threat would require shared data, global decision-making, and a coordinated mission effort. Agencies and researchers already share orbit data and observations through central services. Building clear plans about who leads and how decisions are made shortens reaction time. Exercises and simulations help teams learn how to act quickly and reduce confusion. Detection limits and response plans depend on available assets. Observatories in different regions cover the sky as Earth turns, giving near-continuous tracking when different teams coordinate. Data systems flag and rank moving points so researchers can focus on urgent cases. Some concepts propose small, fast probes that can launch quickly or prepositioned craft ready to change course. Such ideas are technical and costly, but they show how engineering can meet a sudden need. Testing these options improves readiness for many missions. In short, an interstellar object could be dangerous only if its path crossed Earth and if detection came too late. Current capabilities and proven tests show options to deflect short to medium-term threats when found early. The main value of studying fast objects is that they highlight limits in detection and response and push improvements that increase safety for all near-Earth objects. The bigger picture. What these visitors tell us about our place in the universe. Material from another dimension gives direct evidence that small bodies travel between systems. Stars form in crowded regions and can eject objects during early planetary growth. Those objects can drift for long times across the galaxy before a chance encounter brings them near another star. Each object is a sample of material that formed under conditions different from our own, and so helps fill gaps in our view of planet formation. Over time, a larger set of objects will reveal patterns. Scientists will see whether most are dusty, volatile-rich comets, solid rocks, or types that are uncommon in our system. Those patterns will guide theories about how common certain processes are in planet formation. If many objects carry the same kinds of organics or isotopic signatures, researchers can use that pattern to revise models of chemical evolution across the galaxy. Technically, studying interstellar objects also drives instrument development. Spectrographs tuned to certain bands and cameras that can capture faint structures will be more valuable. Data systems that link discovery surveys with rapid follow-up will see increased demand. Engineers and scientists design instruments with these needs in mind, and that work then benefits other areas of astronomy. One idea under discussion is a fast response mission that could chase a future visitor. The main challenges are speed and readiness. A mission would need a fast launcher, a lightweight probe, and instruments focused on quick return data like images and spectra. Another idea is to keep a small, ready spacecraft in a parking orbit that can change course.
With the spacecraft, you just reflect light off it and it's being pushed.
Both concepts require investment, testing, and clear rules about how assets are assigned. At this stage, these are concepts and study topics rather than firm plans. Michio Kaku and other science communicators often place such discoveries in the context of long-term human exploration. He frames the story as part of a broad push to build better tools and to understand the galaxy in different stages. Each interstellar object also gives students and early career researchers a chance to work on real data. The need for quick follow-up provides training in observation, data reduction, and collaborative research. That practical experience grows the community that can respond to future visitors and plan instruments and missions. In short, the scientific value is both in the specific measurements and in the learning process that follows. A close flyby with simple instruments can yield rich data. A camera, a spectrograph, a dust analyzer, and a small mass spectrometer can show composition. Grain collectors can reveal mineralogy and organics. Designing such instruments for fast missions is an active engineering challenge with high scientific payoff and practical mission timelines now. Taken together, these points make clear that interstellar objects are not just created assumptions. They are data points that test models of planet formation and chemical evolution. They drive new technology and give practical training to scientists. As more are found, patterns will form, and our picture of how the galaxy builds its small bodies will become firmer. This interstellar object passed through our solar system on a fast and open path.
It was pushed away from the Sun by some mysterious force.
Telescopes captured its coma, dust tail, and spectra that show common volatile compounds. Observatories worldwide tracked its motion and measured dust production, giving researchers new data about material formed around another star. The object posed no danger and continued outward after its close pass. If you enjoyed this video, leave a comment with questions if you have any or more information that we may not have captured.